Welcome everybody to parallel computing with C++ and scientific computing. Today is the day, finally. We will start talking about parallelism in earnest. I promise you that we will not have any code today, so things are not as tense as usual. It will be more of a broad introduction, terminology, a bit about what are the hardware constraints. We will talk about programming models, and I hope to introduce you to some of the caveats we will face when we want to start parallelizing things. Okay, so let's get going. So I will talk about a bit how the multi-core chips operate, and we referred to that many times. I will just quickly get back to it. How do they get to high performance? How does the software exploit the hardware? That's kind of a topic that is recurring in these lectures. What can we do in the software in order to exploit hardware to the best possible? We will look into the abstractions that we need to use to reason about multi-core systems. We will touch on programming abstractions and mechanisms, some terminology introduction, and in the end, more terminology. So it will be, as I said, a lecture without code, but rest assured, starting next lecture, there will be plenty of C++ code again. Okay, so just to go back to that scheme we showed before, which depicts a multi-core processor as it is built today. Essentially what you have a set of registers here depicted as R0 to R5 and a fetch, decode, read, execute, write loop where that operates on the instructions for that particular core. All of the CPUs we have seen over the last years have essentially this structure, no matter what architecture. Be it x86, be it ARM, being RISC-V, and so on and so on. So each of those runs its own sequence of instructions, each of the cores. On hyper-threading cores, you might even see that they run multiple streams of instructions, but with sublinear scaling, obviously. Each of those accesses its own data, has its own memory hierarchy, its own level 1 caches, possibly shared level 2 caches between cores, and level 3 caches, if they are available, are most of the time shared as well. So each of those cores has to deal with its own memory hierarchy, and that is one of the main aspects of or the main problems we have to face, and we have seen that in many examples so far, that memory is always a culprit. Because executing things is fairly fast, but accessing data from memory is much slower than running the codes. So we will focus on memory and memory structure a lot in this lecture today. So what is parallelism and concurrency? These two terms are used interchangeably most of the time, but just to get us all on the same page, let's say that parallelism can be defined as performing two or more activities at the same time. So these activities may be related in some manner, or they might not be related, right? Two cores can do completely independent things. Two related activities are said to be concurrent if there's no order between them. So if you don't have any defined order between two operations, then you can talk about them to be concurrent, because they can possibly run concurrently at the same time, really in the same moment in time. They may overlap, they may not. In other situations, concurrency is not desirable because a relative order between steps, between operations has to be observed. Because if you want to compute a result that depends on previous computations, then you can't start running that first computation before all the preconditions have been met. So why do we need parallelism? Well, we kind of touched on that already, but if you go back to scientific computing, you will see that all natural processes are kind of parallel by design. Well, nature is not sequential, right? Everything happens at the same time. That's true whether we look at nuclear reactions, whether we look at weather, geological analysis, biological, genetic computation, and so on and so on. All these things are inherently parallel. Modeling these processes requires a highly complex, usually highly complex computations. We have started touching on that. And if you just take one example, if you want to simulate 1 nanosecond of the interaction of just 1 million atoms, you need about 1 billion operations. So 10 to the 17th, 10 to the 18th operations. If you want to do a high detailed week-long weather forecast, you need even more computations. On the other hand, if you look at what a single CPU can do, you will see that it can execute only a few billion operations a second, which is still 1 billion times less than what this atomic interaction simulation would require. So without parallelism, many useful computations would just take longer than the universe before the universe dies its heat death or whatever it's going to die on. Okay, so let's kind of approach that from the grounds up, and let's have a look at what are the different types of computations we see. In traditional software development, you write code for a single core. You create one sequence of instructions, and you want to run that on a single computer having a single central processing unit. And that was a model for many, many years until, well, the early 2000s when people started to introduce multi-core systems. What you do, you have a problem, you break it down into a discrete set of instructions, you make it so that these instructions are executed one after another on a single core. And well, the core can only operate on one instruction, broadly speaking, at a time. So you have a purely sequential execution. Parallel computing is nothing else. You can think of parallel computing as having simultaneously many single computers running at the same time. So you have to break your problem down into smaller pieces. You have a big problem, you divide it into smaller pieces. Each of those pieces is further broken down into a set in a stream of instructions. And these instructions are being executed simultaneously on many CPUs at the same time. Nothing too surprising there. If you look at what parallel computers look like today, you will see that essentially every hardware we have available today consists out of a multitude of processing units. In the simplest case, your iPhone probably has, I don't know, 6 or 8 cores nowadays. So even the smaller phones, even your iWatch has more than one core, so that it can do multiple computations at the same time. We add to that each of the cores consists out of a multitude of hardware elements, floating point units, integral computation units, branch prediction units, and so on and so on. So there's a certain amount of parallelism even inside a single core. And I alluded to that already when I said, talked about hyperthreading, where cores are built in a way that they can kind of partially execute multiple execution streams at the same time, independent execution streams, just by utilizing the different types of hardware that are available. Because one execution stream might need a floating point operation, and another execution stream might need an integral computation at the same time. So these can be done at the same time. So we are working with multiple hardware threads in the hyperthreading scenario. If we extend that to what we call high-performance computing today, what people actually do, they just take a large number of these multiprocessor computers and connect them with a network where the network is very low latency, and we will talk about latencies in a moment, and a very large bandwidth. So it's not as an Ethernet, usually TCP/IP, but there are special networks that have been built just for this purpose to make data sharing between nodes as efficient as possible. So one example would be InfiniBand. There are other examples for these high-speed networks that are used in the large machines we have today, in the really, really big machines. Now you might think the network will connect only nodes of the same type. That is not always true. Most of the time nowadays we have kind of a heterogeneous setup of these systems, that part of the node are special purpose, part of the nodes have GPUs attached or other accelerators attached to it. Nowadays some nodes have quantum computing units that are part of a larger cluster, and so on and so on and so on. So why use HPC? Well, as I said, many reasons. We want to save time and possibly money, because when we throw more compute resources at a problem, we potentially can increase or decrease the amount of time we need to run things, which can be beneficial in terms of economical criteria, right? When a hurricane comes in and you want to predict where the hurricane is producing a storm surge or where flooding will occur, then it doesn't make any sense if the hurricane is 3 days out and you need 5 days to predict where things happen. So you want to be able to rapidly produce the required results, and that requires high-performance computing. On the other hand, these high-performance systems are usually built out of cheap components. It's run-of-the-mill computing components that are connected with a high-speed network. Well, the really leading machines certainly have special architectures and special nodes that are being built just for these computers. But if you look broadly, our development cluster we have here at the group at LSU essentially consists out of normal computers. They have just a different form factor, they're put in a rack and connected with a network, and that's it. So we want to solve larger problems, not only solve them faster, but as I said in the beginning, the problem space and the amount of computations we have to perform in order to solve certain problems are much larger than we can solve, than we need even today. We want to provide concurrency so that multiple compute resources can work on concurrent tasks that relate to the same problem at the same time. And last but not least, there is a question of using non-local resources, cloud computing. So if your own resources are scarce, nowadays you just rent some computing resources somewhere in the cloud, and the same principles apply. And you can extend, and the more money you throw at the cloud provider, the more hardware they give you, essentially. This is a graph that shows you the current leadership machines, how they have evolved over the years from the mid-1990s to today. The data is taken from a website that collects the performance information about the 500 largest machines we have worldwide, top 500. You see 3 graphs. The orange one is the performance of the currently fastest machine we have. The blue line is the performance of the 500th machine in terms of performance we have. And the green line is the sum of all 500 machines in terms of computing power we have. Now you might ask, what is the metric we use to assess performance? Well, it's flops, floating point operations per second. And if you look at the graph, you see that the leadership machines today kind of started to provide us with exaflops performance, which is 10 to the 18th, so roughly a billion floating point operations per second. I'm not sure if we will ever get to zettaflops or even further. We might, I'm not sure, because silicon can't be reduced in size much further down. And the leadership machine that has a bit more than an exaflop consumes, if I remember correctly, about 50 megawatts in power. So you almost have to build a nuclear power station next to these computers. And then you use half of the energy to heat the machine up, and the other half of the energy is used to cool the machine down so that it doesn't melt. And energy grows with the performance because the number of hardware elements grows, obviously. Okay. Just a slide with a bit of terminology. I'm not going to read that to you. If you ever want to know what a certain term refers to, just go back to the slide. Okay, so as I said in the beginning, we will classify or characterize computing systems based on their memory architecture, because memory is the limiting factor in today's computing. So let's start with the simplest computer memory architecture we are dealing with, and that is called shared memory architecture, and that is a basis for shared memory parallelism. That's where multiple processors sit on the same memory and share the memory they work with. By memory, I mean external memory, DRAM. That has the advantage that you have one address space for all the CPUs that provides a user-friendly programming perspective, right? You run one process on the four CPUs. You possibly have 4 threads, and these 4 threads, or whatever threads are running on these CPUs, share the same memory. You don't have to do any special communication. You just work with in the same address space. So it's fast and uniform in terms of data sharing because everything is kind of very close to the CPUs. There are variations to that where you have not one single memory physically, but several memory blocks. Today's computers usually have 3 or 4 memory blocks connected to each of the sockets, where each socket has, I don't know, 64 cores or something like that in the high-performance computing world. And that creates a situation, you still have one address space. So even if you have 2 sockets and you have 2 separate memory units or 8 separate memory units, they still share a common address space. But the further away memory is from a particular core, the more time it takes to access data there. So you have something that's called NUMA, non-uniform memory access, and that is kind of the common architecture we see today. So this is kind of a perfect world picture, if you want. The disadvantages are certainly the lack of scalability, because, well, it's limited by the bandwidth. We have seen that last lecture when we talked about the roofline model, where the memory bandwidth is one of the major limiting things. And the programmer is certainly responsible for correct access to the shared memory. So you should avoid race conditions, all that nice stuff we will talk about soon. The other memory-based computer architecture in the parallel high-performance computing world is distributed memory, where you have not one node, but you have several nodes that are interconnected with a network. And that means that each of those nodes has its own address space. Each of those nodes will run its own processes. And one node cannot directly access memory on another process. So it's a completely different model in terms of programming. So we need communication over a network to connect these interprocessor memories. In other words, when you need to access data that is on a different node, you have to ask the other node, hey, give me that data. So it's a bit more complicated to program. That is kind of schematically. You have separate nodes that are connected with a network, where each of the nodes is a multiprocessor computer on its own. So each of the nodes is essentially a shared memory processor on its own. The advantage is certainly that now we are scalable, because if we need more memory, we just add more nodes. We can grow that up to, I don't know, an exaflop today. And these systems have a large amount of memory available to them. So, and each CPU can rapidly access its own memory without overhead, obviously. And there is no global coherency between the data. So these nodes are not cache coherent. Like inside one system, the hardware is ensuring that the caches are coherent, but across the network, there's no coherency at all. Obviously, the disadvantages are that the programmer is responsible for many of the details of the communication, of the data sharing, of the data communication between nodes. And it's very difficult to map existing data structures to this distributed data structure, where half of your vector is on one node and the other half of the array is on a different node. Now try to program that. So it's not as trivial anymore. And there certainly are hybrid solutions between shared and distributed and shared memory systems. And that is what we see in the largest computers we have today. Each of the nodes is a shared multiprocessor system on its own, and they are connected with a high-speed, low-latency network to ensure communication is kind of efficient. So advantages and disadvantages are obviously the same as before. So whatever is common, both shared and distributed memory architectures, is either an advantage or a disadvantage. You can kind of guess that many of the problems that we had before are the same problems here. It's just that we have a lot more compute power at our hands than with the other systems. And the programming complexity certainly goes up, because now I have to deal with threading on a single node, and we have to deal with data communication across the network with other nodes. From these hardware architectures, we see we can directly derive a couple of parallel programming models. And that is a part that is interesting to us here, right? We don't really care about how our hardware is working. What we want to know is, how do we program these things? What are the facilities we have available to us in order to manage this very complicated hardware architecture? And we will introduce these programming models in detail. Essentially, for one of each, we will have a lecture in the coming weeks. Well, the simplest one is uniform memory. You have one computer, you have one thread, just a sequential execution, no problems there. Shared thread models, where you want to work with many threads in the same application. The typical one is P threads, is the POSIX threads, is the lowest level of parallelism you can achieve. And you will see why we don't want to do that, because it's not pretty. Many people still think it's the way to go, but I think it's not the way to go, and we will see alternatives. A second one is OpenMP, which is a compiler-based solution that can add parallelism to your code without you changing the code too much. We will talk about HPX, which kind of tries to mitigate all the problems of OpenMP and P-threads, and we will see what. There's a whole topic of GPU programming, right? You have these accelerators where NVIDIA accelerators have to be programmed using CUDA. AMD accelerators have to be programmed using HIP. Intel accelerators have to be programmed with SYCL. So each of those accelerator providers have their own programming model you have to learn and you have to deal with. And this is a pain, because each of them is different in one way or another. Distributed memory solutions classically rely on MPI, Message Passing Interface, which is a C library that gives you a communication platform to send data across a network. We will talk about distributed memory programming in the context of HPX, which gives us many benefits over MPI, I believe. There is a data parallel programming model. We will talk about that extensively, and certainly hybrid models that combine things. And here is, in the very first lecture, right, I said this is kind of the hammer or the nails we want to work with in high performance computing, and all of them had different library solutions associated with it. And in the end I said, hey, if we use a custom library we wrote here, we essentially have one environment where we can deal with all of the problems using one interface. And so that's where HPX is really shining in some hybrid context, and we will talk about that towards the end of the course. One term we will use a lot, we talked about SIMD, single instruction, multiple data. In the context of processes, when you have multiple nodes and not a single process anymore, but every node runs its own process, we talk about single program as PMD model, which is very similar to SIMD, SIMD, just that you don't do it on a single hardware, on a single node, but you extend that model to to multiple nodes. In the same way, we will talk about multiple program, multiple data programming models, where each node has its own code and executes the code, and they just interact in some way to exchange data in order to perform the computation. Okay, so a bit more detail about the shared thread models. As I said, POSIX threads. It's a library-based solution which requires explicit use of certain APIs. It's a C library with all the advantages and disadvantages associated with it. Who wants to work with C? I don't. But if you want to work with POSIX threads, you have to work with a C library. It's littered with void pointers on all ends, so you have to really know what you're doing. Otherwise, it's very, very difficult to get right. Most hardware vendors offer a pthread implementation, and that is a benefit. So you don't have to worry about, as a system provider, how to get parallelization done, because the hardware provider will give you a pthread library that you can use to build your own abstractions on top of. So it's very explicit parallelism, requires significant programmer attention to detail. Just an example why I think the pthread model, or in general working with threads directly, is not a good idea. If you look at these really large computers, you will see that they have millions of processing units built in. And if you only have one thread per processing unit, that means that your application has to manage 100 million threads. Most people can't do two things at the same time, not even reason about two things at the same time. So now try to write a program that is doing 100 million things at the same time. So it's impossible to even reason about all of that anymore. And that's why the use of these low-level threads is really not what I suggest doing. And we will provide alternatives that will help us to be able to reason about these highly complex parallel models. OpenMP is a compiler directive-based solution. Essentially, you add hash pragmas to your source code. Things like you slap a pragma in front of your for loop, which says pragma OpenMP parallel, and the compiler will automatically parallelize the for loop that comes after, just in short. It's a standardized API, which is good. It's available for C, C++, and for Fortran. It can be very easy and simple to quickly get some results, but it's very complicated when you want to do very specific things, customize your solution. The downside of OpenMP is also that since it's a pragma, it doesn't know anything about the language it works with. So while it can access variables in the code, for instance, in C++, you can't parallelize a iterator-based loop with OpenMP. The loop boundaries have to be integrals, so have to be integers. Otherwise, OpenMP just doesn't work, because OpenMP doesn't know anything about iterators, for instance. What we will do in this course, we will use higher level C++ standard interfaces like std for each with a parallelization execution policy. And later we will use HPX, which provides extensions to the standard C++ APIs. When it comes to distributed message passing models, you have a set of processes that use their own local memory during the computation. They exchange data, they transfer data in between nodes, and MPI is a classic C library that is the de facto standard for the HPC computing that is used today. We will use HPX for distributed task-based systems, distributed task management in future lectures. Data parallel models are kind of an extension of the SIMD model, as I said, just that we extend that across multiple processes. SPMD models usually rely on a global address space that spans the whole system. So they emulate a global address space that includes all the memories of all the nodes that are connected. And that simplifies programming a lot. And we will see some examples for that in the future. And hybrid models, well, again, HPX is probably the C++ solution that gives you the best hybrid solution that is available today, because it combines all the benefits of MPI, avoiding the disadvantages of MPI. It gives you all the benefits of OpenMP while avoiding the disadvantages of OpenMP, and so on and so on. Okay, so can my code be parallelized? What questions do we have to answer? One question you have to ask yourself, does it have large loops that repeat the same operations? Yes, then we can parallelize it. Does your code do multiple tasks that are not dependent on one another? Yes, well, we can parallelize that. Can any dependencies or information sharing to be overlapped with communication? Can I overlap computation with communication? Then in those cases, yes, we should do parallelism. Do multiple tasks depend on the same data? If yes, well, you might have some problems with parallelizing, but with the task-based programming models we will introduce, we can solve that nicely as well. Does the order of operations matter? How strict are the ordering criteria? All these questions we have to answer. So what are the basic guidance or the basic criteria for efficient parallelization? First of all, you have to ask yourself, is it worth doing? Does a code take a very long time to execute to even start parallelizing it, right? If the code runs for a second, there's probably no point in parallelizing it because, well, you wouldn't even notice even if it ran 10 times faster. Do you run large model or statistics on multiple small runs? Can you distribute these small runs and run them at the same time? Does it make sense to invest the time to parallelize things? Because parallelizing codes is very, well, requires a lot of time, a lot of effort, a lot of experience from the programmer. Is it worth doing that? Or is it just not worth doing it? Will I just spend the rest of my life parallelizing that code that just runs for 3 hours and I don't gain anything? So that's all questions we have to answer. So what we want to do, we want to increase the fraction of our program that can be parallelized to a maximum. And we will see in a moment why that is the case. So we have to identify the most time-consuming parts and parallelize those. We have to balance parallel workload, and we will see in a moment why that is important as well. We have to minimize time spent in communication. Well, if you communicate, we don't do any computation, so we don't make any progress in our application. We want to minimize that. And one of the ways of doing that is by designing code in a way that you can overlap the communication with the computation so that you don't idle your computational resources when communication is necessary. And partition data. How do you partition data? How do you distribute data? What criteria do I apply to split your problem into smaller pieces? Okay, so there are two things we have to consider when we are talking about parallelization. First is the possible speedup. Speedup, I usually use S for it. N is the number of processors we use. So T1 is the time that it takes to run the sequential code. Tn is the time that it takes to run the code on n processors. And the ratio gives you the speedup. Another criteria how you can assess whether your code is efficient is by computing the efficiency, which is defined as the scaling, the speedup, over the number of processors. So efficiency is probably a number between 0 and 1, which tells you how efficient is your parallelization actually happening. So if it's 0, well, then you have no efficiency at all. And if it's close to 1, then you know that you have very nice speedup. So if you have 10 cores and it runs 10 times faster, you have a speedup of 10, an efficiency of 1, which is exactly what you want to strive for. So let's have a very simple example. Let's say P is a fraction of the program that can be parallelized, right? You never can parallelize the whole program. You have some sequential code and you start parallelizing a piece of it. So 1 minus P is a fraction of the remaining sequential code. N is the number of processors. Then the time of running the parallel program will be 1 minus P plus P over N. 1 minus P is the sequential part, and P over N is the N times sped up piece of the code that can be parallelized. If you put in some numbers and say, okay, I have four processors and 80% of my code can be parallelized, then the resulting code will run 40% at 40% compared to the sequential code. So it will run 2 times 5 times faster than the sequential code. Which is kind of surprising, because you run it on 4 cores. Why do I get only 2.5 in terms of speed up? And this is one of the central problems of parallelization. How do I get high efficiency? How do I get to very high speedups when I throw a lot of resources at it? Let's look at that example. I have some, just to explain that. I have some sequential code. The green one is the not parallelizable piece of your code. The 80% is what you can parallelize. You parallelize it, run it on 4 processors. Well, the sequential part stays the same, right? You can't speed that up in any way. But the parallel piece can be sped up by a factor of 4. And that explains why we get only 2.5 in terms of speed up for the problem we looked at. Makes sense. If you make it a bit more realistic and say, okay, it's not just code that is either parallelizable or not, there's some overhead attached to it, I/O, things like that, you know, things you don't have control over. Then we get a bit more realistic example where we see that even if you parallelize things, we have an additional probably load imbalance, because different cores will take different amount of time to work on their piece. Each of the cores has some overhead added to it, and that means that the overall time is even larger than before, and that means that we can't even speed up code to that maximum that I just arrived. So one of the first steps we want to do is to do decomposition. If we have a problem data set that is very large and we want to run it on several compute resources, well, we have to split that data set somehow apart so that each of the tasks can look at part of our data set. In the Mandelbrot example, for instance, right, when you generate that Mandelbrot image, what you can do, you can just say, okay, I want to run it on 4 cores. So you split your image into 4 pieces, and each of the cores will run the code for one of the 4 pieces, which probably will give you some speed up. There are certainly different ways to do the partitioning. Well, you can do block partitioning in 2D and 1D. You can do some cyclic partitioning. And that's certainly the way you partition data certainly depends on the algorithm you want to apply. Sometimes it's more beneficial to do some cyclic partitioning. Sometimes you want to do it line-wise or column-wise in a matrix, and so on and so on. All algorithm dependent. It could be that the problems that you don't want to partition your data set, but you want to partition your problem size, your problem set. The amount of instructions you have to perform can be separated so that everything works on the same data, but in the end, you want to distribute the tasks that work on the data and split that apart so that different tasks will work on different parts of your algorithm, essentially, and all share the same data sets underneath. Okay, so let me skip that, just for the sake of time. So what we want to do, we have to make sure that we load balance our work. We want to split and partition data in a way so that all tasks or all processes require roughly the same amount of time to work on their pieces. Because if one task takes twice as long as the other tasks, you don't really gain anything from parallelizing, because the slowest task will constrain your possibility in speed up, because everybody has to wait for the slowest guy in the very end, right? 2 ways to do that. What people usually do, they try to split the amount of work per task evenly and say, okay, I have 500 iterations. I have 5 cores, so each core will get 100 iterations. That might work. That might not work. In the Mandelbrot case, right, it might not work because each pixel might take different amount of time in order to compute its result. So if you split just by the number of pixels, you might not get very good load balancing. So in those cases, you use dynamic work assignment, where you create a queue of tasks and the threads will pull their work from those queues. And we will see some example of that shortly. Anybody knows that person? Who is that? Anybody? It's Gene Amdahl, one of the godfathers of parallelization. And he has come up with a theoretical assessment of how much can we speed up our parallel applications. And that was later dubbed the Amdahl's law. So let's talk about that a bit more. A couple of definitions. We have the sequential time on one processor is the time that it takes to run the sequential code of the sequential part of the code, and plus the time of the parallel code, right? So that's very straightforward. When we look at the parallel time of the same code on n processors, then you get the sequential time is the same. You can divide the parallel part of the code by n, because that is the part you parallelized. There might be some overhead. For the sake of it here, we will assume that the overheads are 0, just to simplify things. So our possible speedup is the sequential time over the parallel time. So it's the sequential part, parallel part, divided by the time it takes to run things in parallel. If we express that in terms of p, where p is the portion of your code you can parallelize, you get this formula. So that means the best possible speedup you can achieve on a system that runs on n processors, where p is the portion of the code you have been able to parallelize between 0 and 1, you are limited by Amdahl's law. And if you draw that equation, that's the number of cores, that's the possible speedup on a graph. You will see that for instance, for 50% parallelization, you can achieve a maximum speedup of a factor of 2. And it doesn't matter how many cores you throw at the problem. Even if you run it on 100,000 cores, you will not get more than a factor of 2 out of it. On the other hand, if you parallelize 95% of your code, 95%, that means your maximum theoretical speedup is 20. No matter how many cores you have. And that is a real problem, because what's 95%? It's almost all of your application. Try to write an application that is 95% parallelized. It's almost, well, it's very, very difficult, because there is startup, there's I/O, there is communication, there is all kind of things that are inherently sequential, that put sequential pieces in the code execution all over the place. And that will prevent, for Amdahl's law, allowing you to speed up significantly. Just an example where that hurts us. So let's say we have a two-dimensional image, and what we want to do, we want to run two algorithms. We want to multiply the brightness of all pixels, and then we want to compute the average of all the resulting pixels. Both steps take n squared time, right? Because it's n squared pixels. So if we do a parallelization strategy where we say, okay, we execute the multiplication of all pixels in parallel, that will reduce the time needed for the first step to n squared over p, if you have p processors. But we leave the second step, the averaging, we leave that untouched. And that means that our speedup can't even reach a factor of 2, no matter how many processors we use, right? You see it here in the graph. So I can't get faster than a factor of 2 compared to the original sequential execution, just because I leave 50% of my execution untouched. And that's what I said. When you parallelize 50% of your code, in the best of cases, you can get a factor of 2. But if the second step is parallelized somehow as well, and we say, okay, we sum in parallel, combine the results sequentially, then we have some speed up on the second step as well, where we have the first phase, the 2 phase, and then some sequential part that does the reduction over the parallel pieces. And in that case, when n is very large compared to p, we can actually get close to p in terms of parallelization. So be careful with your algorithms. Don't assume that just because you parallelized half of it will give you anything. It will not. As another example, that is a picture of Summit, which is not the top 500 machine anymore nowadays. It was top 500 machine 5 or 6 years ago, possibly. It has about 150 million floating point units across the system. So what is the max speedup if 0.1% of your application is sequential? If you were able to parallelize 99.9% of the application, what is your theoretical speedup you can achieve? What? Well, it's 100. It's easy, right? So you can get not more than, well, no, 0.1, it's 1,000. So even if you have 100 million floating point units, you can't speed up your application by more than a factor of 1,000. And that, under the circumstances that you invested a large amount of time and to get 99.9% parallelization in your application, just to illustrate the problem we have. Okay, so rule number 1 for you to take away: parallelize applications as much as humanly possible if you really want to achieve performance. Well, there's something I call the 4 horsemen of the performance apocalypse, which is 4 things that come in addition to Amdahl's law. Because Amdahl's law gives us a theoretical bound of what is theoretically possible. But there are 4 factors that additionally limit our scalability. And these 4 factors are starvation. If you don't have sufficient parallelism in your system, if you have 100 million computing elements, but you have only 10 tasks that can run concurrently, well, the rest of them starves. So you can't utilize the full power of the machine. Latencies. Time it takes to get things from memory. Time it takes to get things over the network. Essentially, in general, time, distance to services you need in your application. Overheads, it's the work you have to do in order to get parallelism, thread scheduling, thread creation, thread deletion, things like that. And you might guess it already, the last one starts with W, right? Slow. Is waiting for contention resolution, which is essentially the opposite of starvation. If you have more work than the system can handle. If you know a bit about scheduling theory, you know that when you overfill a queue, the response times go to infinity very quickly, exponentially. It's like when you have 3 red lights on Burbank, and the backlog goes down to Lee. This is what is contention, right? Or on I-10, you drive 10 miles an hour, nobody knows why, right? Everybody's driving, things are moving, but you can't drive faster because of contention, right? And this is the same is true for computing systems. If you try to push more work through a system than the system can handle, then everything stops down to a crawl. Very easy to remember, slow. Just call it the slow factors if you don't want to call it the 4 horsemen of the performance apocalypse. People have extended Amdahl's law by adding contention and latencies to it, and what you see is that it not only goes up to a certain asymptotic value, it goes up to a point and then it goes down again when you increase the number of cores. And that is what you really see. When you increase the number of parallelism in the number of cores running on your system, you usually have an optimal performance peak where things run the best. When we first try to parallelize things, we suddenly get a factor of 100 in terms of slowdown compared to the sequential solution, right? And that just means that we ended up on that end of our curve. We added a lot of contention in that case, which prevented us from achieving performance. There are other things that limit things. Just to give you an example, we talked about fork-join parallelism already, where we have several tasks where you can fork out a bunch of tasks, run them in parallel, then you join it again, then you have some sequential piece, then you do another parallel region where you can parallelize things. And already, as you see, there is a sequential piece of code in between 2 fully parallelized loops. And that sequential piece is where Amdahls come along and whacks you over the head. Because you don't see it, you don't have a way to get around it, because you have to join for these tasks to finish before you can start forking out the next batch of tasks. So this is the real problems we have to deal with. fork join parallelism, another problem. Tasks run for different amount of time. If the squigglies are active threads that do something and the blocks are threads that wait for something to happen because they have done their share, you see that there is a large amount of time somewhere in between where threads simply wait for the slowest guy, right? So they have to wait for some operation to finish before they can start parallelism again. And this is where the load balancing problems come in. So even in fork join parallelism, where you think, okay, I have a loop, I parallelize it, great. If the distribution across the cores is not even, you run into additional sequential pieces that are hidden behind the scenes, not visible to you. And again, poor Amdahl comes along and hurts you massively because it adds another 0.001% sequential code to your overall parallelization effort, which hurts you. So the solution here is, and we will come back to that over and over again, is use a programming environment, a programming model that embraces the slow factors, that allows you to at least mitigate part of the slow factors by overlapping things, by doing task dependencies, by avoiding fork join parallelism, and so on and so on. Another person, anybody? No? John Gustafson. The recipient of the first Gordon Bell Prize, by the way. So a very important person. And he created something which is now known as the Gustafson's law. And that is one way around that problem. And I want to show you that because not everything is as bad as it sounds. Let's look at the same problem we had before, right? We have some parallelized code that runs 1 minus p in terms of time in sequential pieces, and p is a parallelized code. And now we look at what is the ratio if we not keep our amount of work constant as we did for Amdahl's law, right? The amount of work was constant, we just added more computers. Here, what we say, okay, I run it on 4 processes, and if I want to compare it to the sequential execution time, I assume that I have only a quarter of the work. So my sequential code has only a quarter of the work compared to the 4-process version. In other words, I increase the amount of parallelism by, and at the same time increase the amount of data I'm working on in a proportional way. So if I run it on twice as many cores, I increase my problem size by a factor of 2. And what happens then is the following. Well, the speed up is this time plus n times the TP, which is the sequential time I would need in order to run 4 pieces of parallel code. And the denominator is the overall time, sequential time plus parallel time, which is 1. So Gustafson's law is essentially saying that the speed up is 1 minus the amount of parallel code I have, portion of parallel code I have in my program, plus p times n, where n is the number of cores. And this is much better, right? Because it gives us a linear, theoretically linear increase in performance, in speed up, when I increase the number of processes. This is what we would like to see. In other words, and that's what most people do nowadays when they talk about parallelization, increase the problem size when adding more cores to it or more nodes to it. And that allows you to actually get almost linear speed up over the number of processes used. So not everything is as bad as it sounds when we talk about Amdahl's law, because there is that famous person, John Gustafson, who has told us that, yeah, we can achieve linear speed up increase if we only increase the amount of work at the same time together with the number of processing resources we add to it, which is good. Otherwise, we would be doomed and nobody would do high performance computing, actually. And that brings us to 2 types of scaling metrics we apply. When you hear people talking about strong scaling, what they're talking about is they have a fixed problem size and they increase the number of cores used to run that problem, and then they look at the scaling behavior. Strong scaling is, as you already guess, very difficult to achieve because it hits Amdahl's law. On the other hand, there is weak scaling. And weak scaling is when people talk about weak scaling, they say, not only I have increased the number of cores to use for my parallel solution, but I have also increased the amount of data I am processing at the same time in a proportional way. And if you look at strong scaling graphs, you usually see something very similar to Amdahl's law, or a maximum which goes down again. If you look at weak scaling graphs, in a perfect world, it's a flat line that is at 1 all the time because the efficiency stays at 1. Okay? Okay, great. I want to do a thought experiment with you. Let's assume we have 1 second of work. And we can split that 1 second of work into 1,000,000 tasks, 1 microsecond each. And we have a system that allows us to run as many of those tasks in a single thread as we want. So on one end, it runs things in one thread, so all tasks are being run in one thread. That means I have a sequential execution, right? Everything is run in one thread. On the other hand, I can schedule 1,000,000 threads and run each of those tasks separately in a different thread. So what do we get? If this is our grain size, essentially the amount of tasks per thread, and this is the execution time, then if you simulate that and just do a simple mathematical model, we get this curve, which is absolutely making sense. 1 means sequential execution time, below means faster than sequential, above means slower than sequential. On this end, we run all tasks in one thread, so we get close to sequential execution time. On this end, things go through the roof because each of the threads has some overhead attached to it, right? If you launch a thread, we have to schedule it, we have to create it, we have to allocate memory, we have to do all these things that are necessary to create a thread. And if you do it once, well, there's a bit of overhead, right? This is this. But if you do it 1,000,000 times, the overheads we pay for each of those tasks we run on a separate thread just go through the roof. And these 3 graphs just show you the simulated results for different amount of overheads. So if I have 1 microsecond overhead, I get this graph. For 10 millisecond overhead, I get essentially something very bad. By the way, this bottom line here is essentially the amount of speed up I get on a perfect world, right? If I have 16 cores, this is probably 16 times smaller than the sequential execution time. And that already tells you that there is an optimal amount of work per thread I have to create in order to avoid going into the end where I'm starting to pay things, right? Where I can't even achieve theoretical increase in performance, or I don't get into the other edge where I have just too little work for each of the threads that make the overheads go through the roof. Does that make sense? So this graph I call the bathtub curve because it looks like this. And if you think about it, it's the absolute fundamental, it shows you the fundamental relationship of overheads in threading systems. So if you understand that graph, you will understand why your performance is bad. As easy as that. So we have to evenly split small amounts of work, and that can benefit from being split into smaller tasks. And we will see here in that graph, in that theoretical simulation, that when you run 10,000 of those iterations in one task, you get actually the best performance. Well, what we have seen is, or the other conclusion is, it has a problem that you don't want to run 10,000 p-threads in order to do that, right? And that's what I alluded to in the beginning. You don't want to work with plain threads because you can't reason about that anymore. Try reasoning about 2 things. My wife claims she can do 2 things at a time. I can't. So I'm trying to come up with programming models that allow me not to reason about this multitude of things that are up in the air, and I have to kind of juggle these balls at the same time. Okay, let's look at that in a real measured system. So this is not simulated anymore, that is really measured. And what you see A very similar graph. This is our sequential execution time. And this is a line where I split the amount of tasks evenly by the number of cores used. So in this case, I'm using 16 cores. So this line corresponds to the point when all cores have the same amount of time, same amount of work. And I run 16 threads. And as you can see, this doesn't even give me the best performance. I get the best performance when I run more threads than I have cores, interestingly enough. And this is an artifact of scheduling, of cache behavior, and so on and so on. So the way I suggested in the beginning to split everything into even pieces and then just distribute it gives you good performance, relatively good performance, but it doesn't give you the best performance. Now you might say, okay, not a problem, I can do that. I can find that minimum here easily just by trying it out. Well, this is a logarithmic graph. So let's turn that graph into a linear one. Then you get this. So now the x-axis is linear. Now try finding this point in order to optimize things to best possible extent. So it's not as easy as it sounds, okay? Rule 3, and that is a basis for all of that, what follows from that graph. Try to allow for the grain size, for the amount of work per thread in your application to be variable, so that you can at runtime possibly decide what is the best amount of work to put on a single thread so that you can optimize the overall performance. And that's where I am today. As I promised, no code, but I hope that you still took away a bit of the issues we have with parallelization, that it's not as easy as it sounds, and there are a lot of aspects we have to simply keep in mind when we want to deal with parallelization. Okay, any questions? A bit quicker and shorter than usual, but I didn't want to bore you too long with all these theoretical elaborations. Okay, thank you. Have a nice Mardi Gras break and see you next Thursday.